Let's dive right into this explainer. Today, we are unpacking a really fascinating and, honestly, deeply consequential study. It's the Vivekananda International Foundation, or VIF, Task Force Report, and it focuses on India's transition to net zero emissions by 2070. Think about the global shift away from fossil fuels for a second. We're talking about the most massive structural change our economies have literally ever faced. It's about fundamentally transforming how over 1 billion people power their lives, their industries, and their futures.
And that brings us to the central puzzle. Seriously, how does a developing nation actually reach net zero emissions without totally sacrificing its economic future? Because India has this incredibly complex dual mandate. On one hand, it absolutely must aggressively fight climate change. But on the other hand, it has a totally legitimate imperative to lift millions of its citizens into higher living standards. You can't just flip a switch to turn off fossil fuels when a massive chunk of your population is still building essential infrastructure and just moving towards widespread electrification.
To really wrap our heads around the sheer macroeconomic scale of this problem, we need to talk about this number, $15.5 trillion. According to mathematical modeling from the VIF report, that is the staggering estimated cost of transitioning India's energy grid to net zero by 2070 if it relies mostly on renewable energy. Just think about that. We are talking about having to raise hundreds of billions of dollars every single year for the next 5 decades.
So to understand how we optimize that astronomical price tag, here's our roadmap for the explainer today. 1. The net zero challenge. 2. The limits of renewables. 3. The case for nuclear. 4. Fossil fuels as bridges. 5. Trillions for the transition. And 6. A balanced energy future.
Starting right off with Section 1, the Net Zero Challenge, Balancing Growth and Climate.
So back at the COP26 Climate Summit in Glasgow, India made some truly ambitious pledges. By 2030, the goal is to hit 500 gigawatts of non-fossil fuel capacity, meaning 50% of its energy will be coming from renewables. And the ultimate target? Achieving net zero emissions by 2070. These commitments represent a monumental, sweeping shift for a country that currently relies pretty heavily on coal for its electricity generation.
But context is absolutely everything here. When we look at projected per capita greenhouse gas emissions for 2030, the story gets interesting. Even though India is the third largest emitter globally in absolute terms, its per capita footprint is just 4 tons. That is a mere fraction of the developed world's output. The US is projected at 13 tons and China at 9. This perfectly illustrates what we call the development imperative. Developed nations essentially used fossil fuels to build their economies over 2 centuries, right? But developing nations like India are now being asked to implement these really stringent emission standards while they're still right in the middle of their growth trajectory.
Moving to Section 2, the limits of renewables beyond the hype.
Now, whenever we talk about clean energy, the conversation almost always defaults straight to wind and solar power. But we really need to look closer at the actual logistical hurdles. Have you ever heard of the term Dunkelflaute? It's this great German word that translates to the dark doldrums. It describes these large-scale meteorological periods where the wind simply doesn't blow and the sun doesn't shine. And we're talking sometimes for weeks at a time across vast regions. Because renewables are entirely weather-dependent, phenomena like the Dunkelflaute prove that an electricity grid simply cannot guarantee stable 24/7 power if it's relying solely on wind and solar.
So the really crucial point the report makes is this. While a solar panel itself might be super cheap, the overall systems cost of a renewable-only grid is extraordinarily high. Intermittent renewables require massive hidden investments. You've got to build huge amounts of standby balancing power that just sits there idle, waiting for the weather to turn. You need massive new transmission lines because, well, wind and solar farms usually built far away from cities. Plus, there are all sorts of costs associated with grid instability. It's a wildly complex and expensive balancing act.
Which brings us to Section 3, the case for nuclear. Clean and firm power.
The VF report's mathematical modeling strongly advocates for nuclear as the absolutely necessary anchor for a decarbonized Indian grid. To understand why, let's talk about the plant load factor. This is basically a measure of efficiency, how much power a plant actually produces out in the real world compared to its maximum stated capacity. Solar PV sits at about 20 to 22%, largely because of nighttime and weather. But nuclear power, it operates at a whopping 80 to 90%. That means a single nuclear plant generates over 3 times the actual electricity of a solar plant of the exact same capacity. It is firm, reliable, baseload power.
Then there's the physical reality of space. India is a densely populated country, right? Land is at an absolute premium. To hit net zero, a renewable-heavy strategy would require a staggering 412,033 square kilometers of land. But by injecting a heavy share of nuclear power into the mix, that land requirement is cut by more than half, bringing it down to just over 183,000 square kilometers. For a rapidly developing nation, saving that much land so it can be used for agriculture and human habitation is absolutely critical. Now you might be wondering, what about the environment? Well, when you factor in the entire life cycle of electricity generation using UN data, meaning mining the materials, building the actual plant, running it, and decommissioning it, nuclear energy actually boasts the lowest greenhouse gas emissions of all these options. It sits at just 5.1 to 6.4 grams of CO2 equivalent per kilowatt hour. That's actually lower than both wind and solar.
But how do we actually manage the decades in between now and net zero? Section 4, Fossil Fuels as Bridges.
It is vital to look at the exact wording used in the Glasgow Climate Pact. It explicitly calls for a phase down of unabated coal power, not a phase out. This was a really pragmatic acknowledgement by major global economies, including the US and China, that abruptly switching off coal would cause catastrophic systemic disruptions and full-blown energy crises. Basically, coal will have to be gradually reduced over time, not just eliminated overnight.
To manage this interim period safely, the strategy relies pretty heavily on natural gas. Step 1 is increasing India's natural gas usage from 6% up to 15% of the energy mix by 2030. Why gas? Because natural gas plants can be ramped up and down incredibly quickly. That leads to Step 2, using this gas to provide crucial peaking power to balance out the highly unpredictable nature of wind and solar. Finally, Step 3 is smoothly transitioning from this fossil-based bridge over into a grid anchored by a firm, clean baseload like nuclear energy, which obviously takes years to construct.
Let's look at the money in Section 5, Trillions for the Transition, the Financial Reality.
We need to look closely at the economic modeling done by IIT Bombay for this report. They modeled out completely different pathways to reach net zero. A renewable-heavy approach, which they labeled R95 and 05, cost that massive $15.5 trillion we talked about earlier. But the scenario that heavily incorporates nuclear energy, known as R05 and 95, brings the total transition cost down to $11.2 trillion. That is a massive $4.3 trillion difference in capital requirement, simply achieved by choosing a more optimal, balanced generation mix. And why does that matter to you or me? Because the wholesale cost of generating the grid entirely dictates your electricity bill. The modeling shows that without the right energy mix, these wholesale prices, often called X-bus prices, could more than triple. We're talking $164 per megawatt hour by 2070 in a renewable-heavy system. If electricity gets too expensive, the widespread electrification of transport and industry simply isn't going to happen, and the entire net zero goal will ultimately fail.
Which leads us perfectly into our final section, 6. A balanced energy future, the optimal mix.
So how do we pull all this data together into a cohesive policy? Well, part of the optimal mix involves hydrogen, a fuel that's going to be crucial for decarbonizing heavy industries. Right now, the push for green hydrogen focuses heavily on using renewable electricity to split water via electrolysis. But the VIF report points out a genuinely fascinating alternative, using high-temperature gas-cooled nuclear reactors. These next-generation reactors can actually split water directly through a thermochemical process using their immense heat, effectively bypassing the whole inefficient electricity stage altogether. This could produce clean hydrogen far more efficiently while requiring way less land.
When you map out the actual installed capacity requirements between the two scenarios, it's wild. The renewable-heavy scenario means building an immense, sprawling infrastructure of solar panels, wind turbines, and giant battery storage parks at a scale that might genuinely just be unfeasible. Compare that to the much more manageable, relatively compact infrastructure build-out required when nuclear power is utilized as the grid's backbone. It is a striking contrast in what we practically need to build in the real world.
So, distilling everything down from the VIF Task Force report, here is the core takeaway. Relying entirely on intermittent renewables is both economically and spatially impractical for a rapidly growing nation. To achieve a reliable grid that enables economic growth while still drastically cutting emissions, nuclear power and pragmatic transitional fuels like natural gas are absolutely essential. It really all comes down to balancing ambition with the hard realities of physics and finance.
And that brings us to the end of our explainer. But I want to leave you with this provocative thought to ponder. As we race to decarbonize our planet, do global climate models and policies need to make much more room for nuclear energy to ensure that equitable economic development remains a reality for everyone, everywhere? It's a tough question, but as the data clearly shows, it's one we absolutely must answer. Thanks for learning with us today, and keep asking the big questions.